This video is about how to organize a data table. This is how the data table looks on your lab report. A data table is where you record the data from your experiment before displaying it as a graph. In IB Physics, all our data tables will look something like this. We can imagine for this video that the data table that we're making is for a lab where we are investigating how the mass of an object hung from a spring affects the stretch of the spring. So in this case, the independent variable would be mass, and I'm going to say that we're measuring mass in kilograms. So the first thing I would record is the title of my independent variable in the top left corner. So you can see I've recorded mass with parentheses kilograms. The reason why I'm putting the unit up there is so I don't have to write the unit next to each individual measurement that I make in the table below. As long as the unit is on the top, I know what all the units of each measurement are without having to write them over and over again in the table itself. And the dV here would be the stretch of the spring, and that's measured in meters, so I'd write that in the dV section. The plus or minus symbol in the data table stands for the measurement uncertainty of that variable. So I can imagine, for example, that I'm using a scale to measure mass that has an uncertainty of 0.001 kilograms, and I don't need to record that unit a second time because it's already recorded under the IV. And I'm going to imagine that the measurement uncertainty of my dV is also 0.001 meters. That's usually the measurement uncertainty on a meter stick. Above the table is a space to put the control variables. You've probably already written down the control variables in another part of your lab. Here you just have to copy them down a second time so you understand what's not affecting the data. So I'm just going to write down some imagined control variables for this experiment. Okay, I'm now going to make up some data. I'm going to imagine that as you were doing the experiment, you were trying to make sure that your independent variable went up by even increments. So I'm going to imagine that you go up by 0.05 kilograms at a time. So this is what your IVs would look like. So you would fill in your actual data here. This is where you would fill in the measurements that you actually took in your lab report. And in most labs that we do, you're going to take 3 trials of the dV for every IV value that you're measuring. So I'm going to fill those in as well. I'm going to imagine that this is the pattern that shows up. The next step after filling this out is to find the average dV for each row, which is really the average dV for every IV value. And the average dV means the literal mathematical average. And you may remember that the mathematical average is the sum of all your numbers divided by the number of numbers that you're adding. So here you would add up the 3 trials and then divide by 3. So in that first row, you would add 0.012 plus 0.010 plus 0.008, divide by 3, and the answer that you get is 0.010. So that would be your average dV measurement for that IV. Usually we record the unit a second time here. The unit of your average dV is the same as the unit of your regular dV. The next step is to fill out the statistical uncertainty. The statistical uncertainty is uncertainty that you have about your data based on how far apart your measurements are from each other. As an example, if I stepped on a scale 3 times and the first time it said I was 180 pounds and the second time it said I was 181 pounds and then it said I was 179 pounds, I would feel pretty certain about my weight. That range of data would give me a lot of certainty because the numbers are so close to each other. Whereas if I stepped on the scale and it said I was 10 pounds and then I stepped on it again and it said I was 1,000 pounds, that would introduce a lot more uncertainty. So the farther away your numbers are from each other, the farther away your measurements are from each other, the more statistical uncertainty you have. So the formula we use to find that statistical uncertainty is the largest number in your range, that's the largest dV in this case, minus the smallest number in your range divided by 2. So as an example, if the largest number in a range were 6 and the smallest number were 2, 6 minus 2 is equal to 4, and half of that is 2. So we would say that if the largest is 6 and the smallest is 2, the full range is 4 plus or minus 2. So that 2 would be the statistical uncertainty. So we're going to take the largest trial minus the smallest trial divided by 2. This is an example for that first row where the largest is 0.012 and the smallest is 0.008, divided by 2, and this is what we get. So those are the statistical uncertainties, and we usually also record the unit that statistical uncertainty is measured in the box above it. Finally, we need to find the error bar values. The error bar values are something that we'll use when we're actually graphing the data. We'll talk about that more in the Logger Pro video. For now, you just need to know that error bars express uncertainty. So when we're drawing error bars, we want to make sure that we're expressing the full uncertainty that we actually have. And that would be the larger of either the statistical uncertainty or the measurement uncertainty of the DV. So whichever number is larger is the one that I'm going to record in my error bar. So in that first row, I can see that the statistical uncertainty is 0.002 and the measurement uncertainty back in my DV box is 0.001. So statistical uncertainty is bigger. So that's what I would record in my error bar value for the first box. And here the statistical uncertainty is always bigger than or equal to the measurement uncertainty. That's just a coincidence for this lab. So I would record those values specifically. I just compare statistical to measurement and see which one's bigger. Here's an example where the measurement uncertainty is bigger than the statistical uncertainty, and so the error bars would be entirely the measurement uncertainty numbers. It's just whichever one is bigger. The last thing that you need to know about data tables is which part of the table you will take with you to your graph, which parts of this table you will actually graph. So this section and this section is the part that you will not graph. The reason why is that these sections really exist to get you to other sections of your data table. The only reason you take the trials is to get to an average DV measurement. And the only reason you find the statistical uncertainty is to get to your error bar value. So these things are not actually going to graph. The IV always goes on the x-axis of our graph, and the DV always goes on the y-axis, the vertical axis. So these values are what you would put on your x-axis. These values are what you would put on your y-axis. You'll want to also label your x-axis with the name of the independent variable and label your y-axis with the name of the dependent variable. In IB, we do something very specific where we give the name of the variable and then put a dash and then put the unit. So we don't use parentheses for the unit. So if I were writing the x-axis for this graph, I would title it mass dash kilograms like that. And if I were labeling the y-axis, I would call it stretch dash m for meters. So this is what that would look like. When you're creating your graph in Logger Pro, you're going to need to add error bars in both the x direction and the y direction. In the x direction, the error bars will just take the value of the measurement uncertainty. And these are the y-axis error bars. So when you calculate error bars, you're really calculating for the y-axis specifically. And that is everything that you have to know about data tables.